Press a button, and a light turns on. That's what you'd expect from any switch. Now imagine a circuit that does the opposite on purpose. Press the button, and the light turns off. Let go, and it turns back on. That's not a mistake. That's the first decision a computer ever learns to make. Last episode, we finished with a switch. A MOSFET, a voltage on its gate, could turn it on or off billions of times a second with almost no wasted current. High voltage we called a 1. Low voltage we called a 0. But a switch that only remembers a 1 or a 0 isn't deciding anything yet. It's just sitting there, on or off, waiting to be told what to do. A thermostat, a calculator, a video game, this very video reaching your screen, none of that happens with a switch alone. It happens the moment a circuit's output starts depending on its input in a way you can actually predict. That kind of circuit has a name, a logic gate, and every single one a computer will ever use, no matter how complicated, is built by combining one basic idea over and over. The simplest version of that idea is the one we're building today, the NOT gate. Here's the wiring. Take one MOSFET, connected source to ground, 0 volts, the reference point every voltage in the circuit gets measured against. Connect its drain to the output, and also through a resistor, up to a positive supply voltage, sitting there ready to push current downward the instant it's given a path. The gate of the transistor, that insulated terminal from last episode, the one that draws almost no current of its own, is the input. Now watch what happens in each state. Input low, 0 volts on the gate, no channel forms. Remember, below the threshold voltage, the transistor stays off, a wall with no path through it. With no way down to ground, the resistor wins the tug-of-war uncontested and pulls the output all the way up to the positive supply. Input low, output high. Input high, enough voltage on the gate to cross that threshold. A channel forms, opening a low resistance path from the output straight down to ground. Now the resistor loses that tug-of-war. It can still push a little current, but almost all of the voltage drops across the resistor itself instead of the output, and the output collapses to nearly 0. Input high, output low. Whatever you put in, you get the opposite out. That's why it's called an inverter, or more formally, a NOT gate. Every logic gate has a truth table, every possible input, and exactly what output it produces for that input. For a NOT gate with just one input, that table has exactly 2 rows, input 0, output 1, input 1, output 0. That's the entire rule written down completely. Keep that in mind going forward. A gate with one input needs 2 rows to describe completely. A gate with 2 inputs, which is what most gates actually have, needs 4. Double the inputs, double the possible combinations. That pattern holds all the way up, and it's part of why the gates coming later in this series get more interesting fast. And every logic gate gets a symbol too, so nobody has to redraw transistors and resistors every single time they want to describe one. That's not just convenience. It's the same idea that lets this whole series climb from physics to silicon to transistors to gates and eventually to code you can actually read. Each layer hides the mess underneath it. The NOT gate symbol is a triangle pointing toward the output with a small circle at its tip. That circle means invert. You'll see it again on the NAND gate, the NOR gate, the XNOR gate. Any gate whose name starts with N, that little circle is doing the exact same job it's doing right here. One thing worth knowing, what we just built, one transistor and a resistor, is the simplest possible inverter, and it's the clearest way to see the idea. Real chips today almost never build it quite this way. They use 2 transistors instead of 1, an NMOS like ours, and its opposite number, a PMOS, which turns on with a low voltage instead of a high one. Wire them so exactly one is ever conducting at a time, one pulling up, one pulling down, never fighting each other, and you get the same inversion, without a resistor constantly leaking a little power, even while nothing is switching. That pairing is called CMOS, complementary MOS, and it's the reason modern chips can pack in billions of transistors without melting. We'll come back to it properly once we've built a few more gates to compare it against. For now, one transistor and a resistor gets you every bit of the idea. Here's what actually matters about this circuit. It's not much of a decision yet. Flip the input, flip the output, that's all it does. But it's the first time in this entire series that a circuit's output depends on its input in a defined, predictable way. Not current flows or it doesn't. A rule. If this, then that. Every if statement in every program you will ever write, at the very bottom of everything, is transistors doing exactly this, just far more of them, wired together in far more elaborate patterns. Every other gate you'll ever meet, or everything a computer will ever compute, is this same basic idea. Transistors, arranged so the output depends on the input in a defined way. More inputs, and a different rule connecting them. One transistor gave us one rule, flip it, but real decisions almost always depend on more than one thing at once. Next episode, we wire two transistors together, not to flip a signal, but to ask a question. Are both of these inputs on at the same time? That's the AND gate, and it's next.